Good morning. I'm Altaf Hussain, former professor, Department of Chemistry, University of Dhaka. Well, we are going to talk about X-ray diffraction techniques. And we start here from X-ray data, how we reduce the data, how we record the data, and come to the conclusion of three-dimensional structure of the said compound. You see, very little was known at the time of discovery of X-ray about internal structure of solids. So, though scientists do believe that crystals have regular external shapes, but they didn't know about the internal structure of the solid or crystals, let's say. It is Max von Laue who was thinking that if crystals are arranged in a regular area of atoms or ions or molecules, it should give diffraction with short wavelength of radiation, such as X-ray. What he did, he took crystals of copper sulfate, where in between the white X-ray source and a photographic plate. To his surprise, he saw a very bright spot in the photographic plate, and as well as some fuzzy spots in the plate. Here you see, this is a very bright spot, and that plate fuzzy spots around the screen. This is the copper sulfate crystals, which showed this arrangement. He then thought that the beam which passes through the crystals is and giving us this fuzzy, strong bright spot, as well as these fuzzy spots. He thought that it should be due to the diffracted beam of X-ray on the copper sulfate crystals. Okay, he was planning how to explain this. Then, at that time, it was well known that light can diffract by a ruled grating. So he thought that if three-dimensional grating theory is can be explained to explain this photograph. So the equation he developed is the angle of diffraction psi in terms of interatomic distance, which he said A, and X-ray wavelength lambda. Then he developed three equations along the three different crystallographic axes. Because at that time, we at least know there are in solid, there are systems, which is three-dimensional crystallographic axes and interaxial angles. So he represented this equation A1 sine psi 1 is equal to lambda 1, which is A. It is in one direction of the crystallographic axis. The second one is the second direction of the crystallographic axis, and third one is the third direction of the crystallographic axis. Then he concluded a diffraction being to occur. These three equations must be satisfied simultaneously. That was conclusion. And with this mathematical derivation, it was a rigorous mathematical derivation, correct derivation, everything was fine. and he was given at that time Nobel Prize for this development or for discovery. But a very drawback was that this is a very cumbersome to use these all three equations and can find out the structure of the crystals as well as mathematical manipulation was a little bit cumbersome too. But the theory he developed, it was mathematically correct, and that what we call Law equation. This three equation is called Law equation, and with the help of Law equation, he could show the structure of copper sulfate. But calculation was very cumbersome, as I said. Then we come to the next equation, which is absolutely used universally. That is Bragg's law of X-ray diffraction. That is an alternative one, and that one is much simpler. So what happened then? This is what is Bragg's law equation we will describe here, and we will go through a little bit slowly to make it clearly understandable. Okay, Bragg's law, it is the father W.H. Bragg and his son W.L. Bragg. Both are New Zealanders, and they were very much interested when that Lau's discovery about X-ray diffraction technique. So they took this and then they determined structure of some crystals. Here we started looking into internal structure of crystals, and pioneer Bragg, father and son. However, though they took interest in Lau's discovery of diffraction, but they didn't take the three-dimensional grating system which Lau did. They showed a much simpler way and based on deflection of X-ray by planes of atoms. Now, I'll show you how to derive this equation, and you will see that it is much more simpler. And this law, Bragg equation is always we use in our data analysis for X-ray diffraction data. Okay, here you see that there are three planes. One is P, another is Q, another is R. This three plane, just we took this three plane. What is this plane? The planes of atoms is in the internal structure of crystals. But we do believe that we have crystals are made of atoms, ion or molecules, regularly three-dimensionally arranged. So we do have planes of atoms in crystals, different types of planes of atoms in crystals, different planes, which we also discussed in the earlier lectures, saying that Miller indices, if you remember, is. So if we have a plane at P, and then again at Q, and then at R, we can show by simple equation that X-ray, we will come to the conclusion with 2d sine theta is equal to n lambda, which is Bragg equation. So how do you do that? Here, these are the incident X-ray beam. It hits an atom in this P plane and diffract. Another incident beam hits atom in the plane Q and diffract. We will see that there is a path difference between these two incident X-ray beam, while they are diffracting. And this path difference is, we can come here, and so this path difference, if we calculate out and we find out it is related with incident angle and lambda. Lambda means wavelength of the incident X-ray beam. Okay, so if we look to this one, and this one, then we see this Q is lower than P. The plane Q is lower than P. Then the beam path, which one is beam path? You see, this is the beam path. We come to B, Y, B, Y, E is the beam path. B, Y, E is the beam path. Similarly, in case of A, X, D is the beam path. And we see this in this two path, there is a path difference. And if we calculate this path difference with this angle GXY and YXH, and we see the path difference, we find out in every path, this is the path difference, and this is GY and GY and YH. This is the path difference for these two incident beam path difference. And this comes out to be, if we take GY in the angle, and then we find out GY is equal to D sine theta. What is D then? Here is the D that we have interplanar distance, perpendicular distance between these two, interplanar distance, we call it D. So GY is equal to D sine theta, and HY is also equal to D sine theta. You can find out mathematically from here. And then if we take path difference, GY plus YH, we get it 2D sine theta. 2D sine theta. And what is this path difference? It is the path difference is equal to lambda. That is meant wavelength of the X-ray beam. Either a single lambda or a multiple of it. So what we are writing, hence 2D sine theta is equal to n lambda. And this is what is Bragg equation. Now we say that it is a much simpler way to show how we get path difference from these incident two beams. And if this path difference are in phase, we get diffraction. If it is out of phase, we do not get any diffraction. So for example, here we show it that these two path difference incident beam and this beam, there is a path difference, and these two incident beams are in phase. If that would be out of phase, we do not get any diffraction spot. That's what discovered by two Bragg's father and son. And for this, they will be always remembered while people are working with X-ray and X-ray crystallography. So any type of crystallography. Okay. To get this, we have been doing many other terminology, for example, crystal lattice, planes, and direction of planes, these sort of things we have been discussing earlier. But one very important term we didn't yet talked about. It is reciprocal lattice. We were talking always about direct lattice. We showed the parameters for direct lattice. We also defined various crystal systems with direct lattice, but we never yet discussed any term calling reciprocal lattice. Now, we have to understand why reciprocal lattice is so important to us. So, reciprocal lattice, or it is also called K-space. It is an essential aid. What sort of essential aid? Understanding and interpreting single crystal diffraction data. So reciprocal lattice, we need it for interpreting or reducing single crystal X-ray data. If you remember, we said about two type of crystallographic data we can get specifically for X-ray, the X-ray diffraction data, X-ray powder diffraction data, X-ray single crystal data. So for powder diffraction data, we may analyze the data using direct lattice type. You might ask then why not single crystal? You will see that why not single crystal in the next slides. Why not single crystals? In powder crystal data, when you get a peak, it is an average of same family planes. You get an intensity average of same family planes of plane. But in this case, for single crystal data, we will see that it's not average. It's every Miller indices give spot. And we have many data for single crystal to analyze this structure. Okay, this is the first point. To understand and interpreting single crystal data, we use reciprocal lattice. We'll come to later what is reciprocal lattice, then how we construct a reciprocal lattice. That will come. And another thing that this reciprocal lattice using the band theory of solids. These are the main two things we use with the reciprocal lattice. Therefore, in crystallography or in material science, very much useful term, reciprocal lattice, we have to understand. I said, in terms of unit cell lattice type and crystal symmetry of crystal structure, we will be using this reciprocal lattice. The concept of reciprocal lattice was introduced. The number, orientation, and interplanar separation depends solely on the geometry of the unit cell. X-ray regarded as diffracted or reflected from these imaginary lattice planes, which we called which we show a little bit earlier. That we imagine that is a P plane, P sets of plane, Q sets of plane, R sets of plane, and then with this imagination we start describing our data. This provides the real space description of XRD. Amra jokhon when we explain real space the description of XRD, that's what we did with imaginary lattice planes, etc. Direction of incident and diffracted beams are related to the interplanar spacing. We showed in the last slide, and X-ray wavelengths by Bragg law. For many purposes, it is advantageous and convenient to treat this direction in terms of reciprocal space. Specifically, I say single crystal diffraction data. We need it. The manipulation of crystal lattice in real space. It allows us to identify the so-called reciprocal lattice, which then becomes particularly useful for discussing single crystal diffraction data, especially those obtained using transmission electron microscopy is another technique. We were talking about different techniques of analyzing crystals. So one technique is when we do get data by X-ray diffraction. Another technique, I told it, we do get data by electron diffraction data and then neutron diffraction data. So what the reciprocal lattice, when we want to determine structure of solids, we take the data, single crystal X-ray diffraction data or transmission electron microscopic data. Next few slides, what we do, we will show how we can relate real space data and the reciprocal lattice data. That's what will be shown in the next few slides. The reciprocal lattice is derived from its real space counterpart. How different crystal system, lattice type, and space symmetry elements have characterized. Characteristic feature in the reciprocal lattice, that's what we also discussed. And then diffraction is described using the reciprocal lattice. That's what we do. We have been using diffraction, but not with reciprocal lattice. It was just Bragg equation, real space data, Bragg equation. But now we'll see that we can describe also with Bragg equation the reciprocal lattice system. As I said, that we have to see how real space lattice and reciprocal lattice correlate each other, and we can relation between these two has to be taken into consideration to reduce X-ray data, and that's what I take in next lecture. Thank you for this lecture, and I again repeat that these two slides are very important slides, what we discussed, and we have to remember that while we are reducing X-ray diffraction data. Thank you all once again.